So, hello everyone who's watching on YouTube. Since no one has joined the session in person yet, I'll just wait for like 5 minutes before starting this summary session. So I'll get started in 5 minutes. I'll be waiting for a few people to join in person as well. I'll be muting myself till then. Okay, so since no one has joined the session in person yet, I guess I can just get started with discussing the today's session. So first of all, just to reintroduce myself for the last time in this course, everyone. So hello, I'm Lakshya. I'm the discrete maths and PTLTA for the Monday 6 to 8 p.m. sessions. And this is like not the one of the regular problem solving session. This is a summary session basically. And in this session, I won't be discussing any problems, but rather I'll just be going over all the problems that we have discussed over the course of 12 weeks. Not the problems, but more of the concepts which we have covered. So this will serve more as a revision session for everyone per se. So I have a bunch of notes, a bunch of like important like revision notes, let's just say, prepared for so that we can discuss like what all have been covered in the 12 lectures. So I'll just share my screen and I'll just go through those notes so that everyone like these can act as a quick revision for everyone. Note that like these are not substitutes for the actual lectures, obviously, since these just contain uh, very less information as compared to the actual lectures. But yeah, these are just for more or less quick revisions. I'll just share my screen and I can start discussing them. Okay, I hope my screen is visible since I don't have anyone in the actual meeting to confirm it, but I'll just be assuming that my screen is visible to everyone. So yeah, so this is the session 13, and this will be once again just our last session. So I have like week notes for week by weeks prepare like what all have been the crux of what all was discussed in the lectures during week per week. So I guess we can just get started with discussing these. So in the first week, we kind of saw that the first session which we had, the first set of lecture was more about just recollecting what all we had done in high school regarding discrete mathematics, some more advanced stuff than high school, but more or less the same counting principles. So we had discussed counting, binomial, multinomial theorem, and what are Catalan numbers, these were something which were new and pretty cool to us. So per se, so just what are permutations? So usually like permutations are denoted by NPR, and this just means the number of ways in which R items can be selected and then ordered out of N items. So what this means is that suppose we are given N items and we have to select R of them and then permute them also. So note that in permutations, ordering also matters. If we just have to select the items, then it was just combinations. But if we have to select and then like order them, then it's what we call permutations. And this is given by like n factorial divided by n minus r factorial. So if I want to select r items and then permute them out of given n items, the formula is this n factorial by n minus r factorial. And this can be easily derived also because you can just see like first item that the item which we first pick can be built in n ways. The second item has only n minus one ways now. Because the third item has n minus two ways. And since we are selecting r items, the rth item to be selected will have something like n minus r plus one choices. So multiplying all of these, we get somewhat of this expression. But note that obviously here the ordering matters because the set of items, let's say there are n items and we select the items 1 to r. Then the ordering 1, 2, 3 till r and r minus 1, r minus 2 till 1. These two will be counted as differently in these permutations. So if we don't want to distinct between these, if we don't want a distinction between these orderings, that we want all orderings to be counted as the same, then that's what we call combinations. And combinations are just the number of ways in which our items can be selected out of n items. So we don't need to order them, we just need to select them. And this is given by n factorial by r factorial times n minus r factorial, and it's denoted by NCR. Some people like refer to it in these sorts of notations, also parentheses notations. But yeah, these are also known as NCR. So yeah, like how did we arrive at this? So it's not too difficult. So first of all, if in permutations we select like if there are these n factorial by n minus r factorial ways in which items can be picked and then ordered, then we just need to remove the ordering factor from this, right? And if there are r items and we need to order them, they can just be ordered in r factorial ways. So we just need to divide this quantity by r factorial to find out the number of ways in which r items can be selected. And that's what we do. So we do what we do. We take this n factorial by n minus r factorial, the number of permutations, and divide it by r factorial. And this is what gives us the combinations or the number of ways to select it per se. And now, then we also covered binomial theorem. Binomial theorem is also somewhat what we have already seen in high school also. And there was this generalization of multinomial theorem, which is like more or less binomial theorem only, just for more number of variables. So binomial theorem says that like it's not too hard to derive it yourself also, but just for the sake of completeness. So if we have the expression x plus y and we raise it to the power n, then x plus y raised to the power n can be written as sum of like n plus 1 terms. So TR denotes the rth term and r goes from 1 till n plus 1. So x plus y raised to the power n is denoted as sum of these n plus 1 terms, where the rth term, the TRth term, is given by n choose r minus 1 times x raised to the power n minus r plus 1, y raised to the power r minus 1. So note that uh, the deriving this expansion is not too difficult. Like this is just basic counting mathematics, but note that this is something which we need to still remember. Like remember in what sense? I think I discussed it in the problem session itself also, that the defining TR is somewhat of a notation for us. Like the coefficient term of the term y to the power. So the term involving this y raised to the power r minus 1 is what we call the TR term. So note that like if someone does not know the convention, one thing can think, oh, why am I calling this term like uh, the algebraic which contains the algebraic part as this x raised to the power n minus r plus 1 times y to the power r minus 1, this as the TRth term. Why can't I define like x raised to the power r minus 1 and y raised to the power this coefficient as the TRth term? That I want to write it like in terms of x. The TRth term is just the coefficient of x raised to the power r minus 1 rather than y raised to the power r minus 1. But know that like I don't have any concrete answer for why is this the case, that like why we choose y to the power r minus 1 and not x to the power r minus 1 as the rth term. So note that it does not change the actual formula value, because like the actual formula value won't change uh, because like the expansion remains this itself, but like defining what this TR specifically is a matter of notation. So this notation has been universally adopted, that we'll say that TRA term is like the term which has y raised to the power r minus 1 as one of the terms, algebraic terms. So I hope this makes sense. So that's why like the coefficient is not too hard to see. Like if you have y raised to the power r minus 1, then out of these x plus y raised to the power n expressions, you need to choose y in r minus 1 of those. So that's why you have this n choose r minus 1 factor here. This factor is not difficult, but like this notation is something which we need to remember, that TRH is the term with coefficients of y raised to the power r minus 1, something like that. And then after this came this, like after that, like this was more or less what we already knew from high school. And after that, this came up like these Catalan numbers are something which I personally find very cool. And how do we define these Catalan numbers? So the nth Catalan number is just defined as the number of ways of going from a bottom left to top right of a n cross n square grid. So this has been so like suppose we have a square grid of n cross n size, and we need to move from the bottom left to the top right of the square grid. So like suppose this outline is a square grid, although it's a rectangle, and it's an n cross n grid. Then I need to move from this point, the bottom left point, to the top right of the point by moving only one step right or one step up at a time, and without crossing the diagonal. So note that if we were not given this restriction that we can cross the diagonal, suppose we are not given this restriction that we just need to find the number of ways of going from bottom left to top right of n cross n square grid by moving one step right or one step up, then it was rather an easier problem, because for that what we can do, we can just say that, oh, I need to just take n right steps and n up steps, and I can do these in any order. So So there are n right steps and n up steps. And in how many ways can I arrange these amongst themselves? So this will just be like n plus n choose n. So it would come out to be 2n choose n if the problem was just this much. But now there is another restriction that we should not cross the diagonal. So the problem asks us without crossing the diagonal of the square. So if we are not crossing the diagonal, like then the problem becomes a bit more involved. Oh, how do I see that? The diagonal is effectively the primary diagonal, like the one which goes from top left to the bottom right. And then how do I do this? And like so it was discussed in the lectures, also the derivation for the same, that this comes out to be 2n choose n. So these were the total number of ways. And from these ways, this 2n choose n minus 1 is what we subtract. So note that these are the total number of ways in which we move from bottom left to top right. And from that, we subtract a quantity so that we arrive at the number of ways in which we move from bottom left to top right without crossing the diagonal. So actually what this corresponds to, this 2n and choose n minus 1, this 2n choose n minus 1 is the number of ways in which we can move from bottom left to top right while crossing the diagonal. So see, the total number of ways is 2n choose n, and they would be made up of the number of ways in which we cross the diagonal plus the number of ways in which we don't cross the diagonal. And this formula was like discussed, and its derivation was also discussed. So the number of ways in which we do cross the diagonal comes out to be 2 and choose n minus 1. Suppose a question comes which asks you just like number of there are how many number of ways will we actually be crossing the diagonal? Then the answer would be 2 and choose n minus 1. And this 2 and choose n minus 2 and choose n minus 1 is the number of ways in which we don't cross the diagonal. And this you can like find this, that this will also be equal to this 1 upon n plus 1 2 and choose n. You can just expand this out and see further so that these formulas are equivalent. So nothing new here. And then yeah, so some of the applications of Catalan numbers can be, suppose you have to put n plus ones and n minus ones in some order, like you have to add them in some order such that their sum always remains positive or something like this. So like you have to put a sequence of plus ones and minus ones in some order such that the running sum, like the sum from the starting number to the ith number for any I, remains greater than equal to 0. Then that can be considered as a Catalan number problem itself, right? Because like you can think of plus 1 as going to the right and minus 1 as going up. And then what you want to do is you don't want to cross the diagonal. So that's how it comes out to be like this is equivalent to like sum of plus ones and minus ones, this Catalan numbers. This Catalan numbers has various number of applications. That is very good. So yeah. And after this, we have in the second week, we discussed basically second week was more of an introduction to set theory and De Morgan's law. So, uh, so what's a set? A set is just a collection of well-defined objects. And note that these objects can be sets itself. Like a set can consist of objects where these objects are also sets. So well-defined objects just mean like any object. In that sense, sets are pretty cool. And what's a power set of? And note that usually in a set, when we define a set, we just say that all the elements of a set are distinct. So it's a collection of well-defined distinct objects. There is something what is known as a multi-set also, in which the elements of the elements can occur, like objects can occur with repetition also. But for now, we'll just be sticking to the definition as distinct objects. And a multi-set specifically says that a set in which elements can occur multiple times. Then power set of a set is nothing but we define power set of a set as just the set of all possible subsets of that set. So I hope everyone understands what a subset is. Okay, I'll search for this. So a subset is just like some elements taken out of the set, and that's what we call a subset. And so set of all possible subsets is called a power set. And you can see that the number of possible subsets of a set is just like 2 raised to the power cardinality of S. And this is because every element of the set we can either choose in a subset or we don't choose in a subset. So there are two choices for every element. So that's why it comes out 2 raised to power cardinality of this. And note that this is, I hope everyone knows this already. So this is, I did not introduce I did not write what a cardinality of S is, but it's just the number of elements in the set S. And I think this is quite well known. So yeah. Then we came to like De Morgan's laws, and De Morgan's laws are basically just you can see these easily using set theory. Also, like you can draw a Venn diagram, and from that you can understand. But all in all, just what do De Morgan's laws state? So if you have a set A union B and you take its complement, then it can just be written as A complement intersection B complement. And similarly, if you take A intersection B and you take its whole complement, it can just be like simplified to writing as A complement union B complement. So like not very technically involved, but yeah. So like just so this just gives us a general formula of like or a general algorithm of how to define a complement. Like if you have to take A union B whole complement, what you can do is you can just you can just replace all the unions by intersections, all the intersections by unions, and all the variables by their negations. So A will be replaced by A complement, B will be replaced by B complement, all unions will be replaced by all intersections will be replaced by all unions. And voila, we have this is an equivalent formulation for the whole complement of it. Okay, then in third week, we started discussing about Boolean logic. So, and in Boolean logic, we like first discuss what do we mean by statements, what do we mean by propositions, etc., etc. And I hope everyone remembers what are these. So, propositions are statements whose value is always either true or false. Like they can't like they will always be either true or false. They can't have any third thing. Like, and we saw like there are like statements which are not propositions. Like there are statements which are vague and they necessarily won't be either true or false. Or, yeah. And then what's a tautology? So tautology was defined as a proposition which is always true, regardless of the values of the Boolean variables it takes. So a proposition like regardless of so usually if you have a Boolean formula of variables and if it always evaluates to true, regardless of the Boolean variables involved, then that is what we call a tautology. That this statement will always be true. And an example for this is P or not P. And why is this a tautology? So suppose P takes the value true, then true or not true will always evaluate to true because like in our function, if any one of the arguments is true, then the whole like the whole function evaluates to true. Similarly, if P was false, then not P becomes true. And then again also this whole P or not P becomes true. So that's why like this is a tautology. Similarly, like there was some we defined also what's a contradiction. I did not write it here. So contradiction is a statement which is always false. Suppose I replace P or not P by P and not P. Then that statement is actually always false. You can see for yourself why is that the case, and that is what we call a contradiction. And then we arrive and then we discuss what are De Morgan's laws for Boolean formula. So this A union B and A intersection B, like you get like these can be like so this De Morgan law in terms of set can also be extended to De Morgan law for Boolean formulas. So here the negation operation corresponds to the not, the or operation corresponds to the union, the and operation corresponds to the intersection. So and then it's the same thing. So not of a Boolean formula P or Q. Suppose we are given a P or Q Boolean formula, and we have to take not of, and we have to take negation of this whole formula. Then this is just equal to not P and not Q. So just replace all the ors by the ands, P's by not P, like and all like basically replace all the Boolean variables by their complements, all the ors by their ands, and all the ands by their ors. And we have we have an equivalent formulation for the same formula. So like here we can see that if we want to take not of P or Q, then you just take not P and not Q. Similarly, if you want to take note of P and Q, then it is just not P or not Q. So I hope everyone sees the correspondence of the De Morgan's law for like Boolean formula and De Morgan's law for the sets. So yeah. And after that, we discussed like what are relations. So a relation over the sets A and B is nothing but a subset of the set A cross B. This is the content of the fourth week. So in fourth week, we discussed like what exactly is a relation. And a relation is defined over two sets. So if we take two sets A and B, then any subset of the set A cross B. So A cross B is just the set product. I hope everyone knows what this is. So, and then like if we take a subset of A cross B, then that is one relation. Like any one subset will correspond to one relation, another subset will correspond to another relation, and so on. So yeah, these are what we call relations. And then we had these definitions of what's a reflexive relation. So a reflexive relation is a relation in which so suppose like uh yeah. So suppose we are defining this set like suppose if we take the sets A and B to be equal, that we define that relation. Suppose if we take a relation and we say that it is just over the set A cross A, then with respect to that we can define what's a reflexive relation. And reflexive relation is just a relation in which suppose there is in which small a comma small a belongs to the relation for all small a belongs to the capital A. So what this means is that you take any element of the set capital A, then and we know the total set like after which the relation is formed is the set capital A cross capital A. So if we take any element small a, then the pair small a comma small a should belong to that relation. If this is true for all elements of the set capital A, then we know the relation is reflexive. And then what's a symmetric relation? Symmetric relation is if A comma B belongs to the relation R. So note that relation is just a subset. So if A comma B is an element of this subset, then B comma A should also be an element of this subset. If this is true, then it is what we call a symmetric relation. A comma B belongs to R implies B comma A belongs to R. So yeah. And then we have this transitive relation. And how do you define transitive relations? So like these definitions, like they might seem tedious, like but they are like sort of simple. And I believe like everyone should know like at least these three definitions everyone should know like what's a reflexive, what's a symmetric, and what's a transitive relation, because these have various applications in computer science a lot. So yeah. So if A comma B belongs to relation R and B comma C belongs to relation R, then A comma C should also belong to a relation R. And if this is true for like all possible A, B, C, then that's what we call a transitive relation. That's when we call a relation a transitive relation. And then what's an equivalence relation? So these are the most important relations for us in computer science. So these are relations which are symmetric as well as reflexive and as well as transitive. So a relation which is symmetric, transitive, and reflexive, all of these three at the same time is called an equivalence relation. So yeah, and these are pretty cool. So then we came in the fifth week to discussing functions. And what are functions? So function is nothing but a relation. Like function is like a type of relation with some more special properties. So a function is a relation where every element of the domain is mapped to exactly one element of the codomain. So in relate like with respect to functions, if we have these sets A, so suppose we have a relation like oh a relation is a subset of the set A cross B, right? And the subset which we take in that we can define the domain as the elements of the set A and the codomain as the elements of the set B. Like, I hope everyone uh, I hope everyone knows what a domain and a codomain is. So like domain is all the values which the input variable can take in a function or something like that. And codomain is just the set out of which the function can take values. Like so input values correspond to something like domain and output values correspond to something like codomain. So something like that. So a function is a relation where every element of the domain is mapped to exactly one element of the codomain. So note that in a relation, suppose relation is over the set A cross B, we don't have any restriction that suppose an element 2 comma 1 and an element 2 comma 2. Both of these can be part of a relation. But note that both of these cannot be part of a function. Because in a function, what we have an additional property is that it's a relation, but every element of the domain, and domain is like the set A part, should be mapped to exactly one element of the codomain. So if we have an element 2 in the domain, then it can only be mapped to exactly one element of codomain, like not less than one, not more than one, exactly one. So like in a function like 2 comma 1 and 2 comma 2, both of these elements cannot be present, because if that's the case, then like 2 has been mapped to like two different values, 1 and 2. So that's why it's not a function. So function is a special relation in which every element of the domain is mapped to exactly one element of the codomain. And note that like there's a difference between codomain and range of a function. So range of a function is like the set of all possible values that the function actually takes. And codomain is the set of possible values from which function can take. Like, there's a slight difference between domain and codomain, and like I hope everyone knows what that is. And then we define what are one-one functions. So what are one-one functions? One-one functions are the functions like intuitively what are one-one functions. So they say that each output will correspond to exactly one input. So uh, so we saw that in a function like every input is mapped to exactly one output. But if the other side is also true, that any output of the function which the function actually takes is mapped to exactly one input, then that's what we call a one-one function. And formally it can be written as follows, like if f of a is equal to f of a prime, then a should be equal to a prime. Like there should be no other value of a prime such that f of a is equal to a prime other than the value a itself. So this is the formal definition of one-one function. Similarly, what's an onto function? So onto function is a function where every element of the codomain is mapped by some element of the domain. So note that like I earlier told, like you guys must already know also that domain codomain is the set of elements from which the output values can take, and like range is the set which the function actually range is the set of values which the function actually takes. There's a slight difference there. And so effectively, if range of a function is equal to its codomain, like intuitively, then that is what we call an onto function. And this can be written as like every element of codomain is mapped by some element of the domain. Because if it is mapped by some element of the domain, then that element is also something like in the range of the function. So this statement is equivalent to saying that range of the function is equal to codomain of the function or something like that. So we have defined what are one-one functions, what are onto functions. These we have like studied in high school also, but still. And then why do we need these? So we have another interesting concept which are like invertible functions. And what are invertible functions? A function is invertible if and only if it is one-one as well as onto. So yeah. So formally, like we can just say that a function is called an invertible function when it is one as well as onto. But like, what's the intuitive sense of it? Like, why do we even need these invertible functions? This you might already know that. So that like in invertible functions, like there always exists an inverse of an element. For every element, there exists an inverse. So like for uh every element x, there exists an inverse which we can call like f inverse x, such that f of f inverse x comes out to be equal to the identity or something like that. So I hope everyone knows what this is, what this is about. And then afterwards in the sixth week, like there in the sixth week, like 6 week, like there were no very specific concepts covered, but more of very general mathematical concepts, which which these might be very general, but they do have very far-reaching consequences. So we discussed something like the principle of mathematical induction, and in this like mathematical induction is also two types, like strong induction and weak induction, and like you guys must already know, but on a high level, what we do in mathematical induction is if we know some. So these are more. So mathematical induction and pigeonhole principles are more or less methods to prove something. Like if these are more of a like general arguments, general frameworks using which we can prove some statements. So like so suppose if we are given a statement and we want to prove it that this statement is actually true, then one way is to do mathematical induction. And mathematical induction, like the general framework is as follows, that we say that suppose the statement is true till like some first n values or like still some set, and then we say suppose it is true till some set, and then does there exist any value outside this set also for which the statement is true. Like suppose the statement is true till first n numbers, and then we say whether this using this idea, that using this as a hypothesis that the statement is true for first n numbers, if the statement true for the n plus 1th number also. And in this manner, like we try to prove the argument, and this is what we call mathematical induction. And we discuss some like question regarding the same also. And then there's this concept of pigeonhole principle, which was also covered. So pigeonhole principle in itself seems like a very basic and naive thing. Like so what does pigeonhole principle say? That suppose there are n pigeonholes and like n holes and n plus one pigeons. So suppose there are n holes like in a building, and like pigeons have to sit in those holes. But if we have n plus one pigeons, then there will exist at least one hole in which two pigeons are sitting, right? And it's quite of obvious because there are n holes, and like maximum per hole, if we give like one pigeon to every hole, then there will be just n pigeons, and then n plus one pigeon will have to go in some hole, uh, which is already occupied by a pigeon. So that's why there will always exist a hole which has two pigeons in it. So this seems like a uh, pretty like simple argument, but this does have like very interesting application, one of which we also discussed in the problem solving sessions, a question which I really like a lot. So there was this question like suppose we want to prove that there always exists some numbers a comma b such that 2 raised to the power 2 raised to the power a minus 2 raised to the power 2 raised to the power b is divisible by, let's say, the number 5, or let's say the number 10, or something like this. So this is something which we had already discussed this problem, but like yeah, pigeonhole principle, even though it might seem very naive and obvious, but it does have very interesting applications. Okay, then after that, in the seventh week, we discussed more or less the concepts of graphs as well as trees, like what are graphs, an introduction to what are graphs and what are trees, and like some theorems also regarding them. So what are graphs? Graphs are just a collection of vertices and edges over the vertex head. So yeah, pretty easy. And then there was this handshaking lemma, which was discussed for graphs, and which just says that sum of all degrees of all vertices is equal to twice the number of edges. So this is not exactly the handshaking lemma. So what does handshaking lemma say? So like, but the handshaking lemma is equivalent to at least this statement. Like at least this statement is stronger than the handshaking lemma. So this is kind of obvious that sum of degrees of all vertices is equal to twice the number of edges. Like because like in sum of degrees of all vertices, like an edge always appears twice, because like if there is an edge x comma y, then it appears on in the x side, like when we are counting the degree of x, and also appears when we are counting the degree of y. That's why every edge appears twice in this sum. So that's why it is equal to twice the number of edges. And then like we can also break this down into like sum of degrees of all vertices can be broken down into sum of degrees of all odd degree vertices. So all vertices can be broken down into vertices having odd degree as well as even degree. So it can be broken down into two parts. And then what we have is sum of degrees of all odd vertices plus sum of degrees of all even vertices is equal to twice the number of edges. And note that this is an even number. And note that sum of degrees of all even vertices will also be even. And so what we are left with is that sum of degrees of all odd degree vertices is always even. So this is what handshaking lemma says, that sum of degrees of all odd degree vertices is even. And when is sum of like sum of odd numbers equal to an even number when the number of odd numbers is even. So equivalently, like what? So in a nutshell, what does this say? The handshake lemma says that the number of odd degree vertices is always even in a graph. There cannot exist a graph which has odd number of odd degree vertices. So, yeah. And then we discuss Havel-Hakimi theorem. Like, this is a very good theorem for my opinion. Like, so this is more of a graph realization problem. Like, what are graph realization problem? Suppose we are given a sequence of numbers, and suppose we are posed with the problem that can this sequence of numbers correspond to degrees of vertices of some graph? So does there exist a graph for which a given sequence of numbers corresponds to like degrees of that graph? And Havel-Hakimi theorem tells us like how do we answer this question. So what Havel-Hakimi, like all these numbers, the degrees in their decreasing order, and then like suppose the greatest number is, let's say, x. So what we do is from the next x numbers in the list, we reduce all the next x numbers in the list by one, and like something like this. And this procedure we somewhat keep repeating, and like till we arrive at a very trivial case or something. But it is very important to note that in Havel-Hakimi theorem, we always have to sort the sequence which we are given in descending order. And note that we have to do this in every iteration of Havel-Hakimi. So this is a very common silly mistake among students that what they do is they initially like order the degrees in the descending order, but after that they just forget to resort again, because if you are reducing some numbers by one, if you are reducing some number, then the sorted sequence can change. But if you don't resort the sequence, then you won't know if it has changed, and you can come up with wrong answers in that case. So at every step, one should be sorting these numbers. So yeah, always remember to sort the sequence in descending order every iteration. And then we also discuss what are different types of graphs. So there are cycle graphs, path graphs, regular graphs, and so on. There were different kind of definitions, and like I hope everyone is familiar with them. And then we discuss what are trees. So tree is a connected graph which does not contain any cycle. So a connected graph which does not contain any cycle, so basically an acyclic graph, but connected, is called a tree. And it's easy to show that a tree with n vertices will always have exactly n minus one edges. Because if there are less than n minus one edges, then it cannot be connected. And if there are more than n minus one edges, then it will necessarily contain a cycle if it is connected. Something like that. So a tree with n vertices always has n minus one edges. And then we discuss what are cut vertices. So cut vertex is a vertex whose removal disconnects a connected graph. So if we are given a connected graph, or let's say a connected component, and if we uh, delete one vertex such that the component gets like disconnected, like there become more two or more components in the graph now, then that is what we call a cut vertex. And similar definition can be defined for like cut edges also. So cut edge is an edge whose removal disconnects the connected graph. Like yeah. So in these, one thing to note is that like I think I discussed this during the sessions also, that if a graph contains a cut edge, then it does not necessarily mean that it contains a cut vertex. And the opposite is also not true. If it contains a cut vertex, then it contains a cut edge. So these two are not stronger or equivalent to each other in any sense. So there exist examples of graphs in which there exists a cut vertex, but there does not exist a cut edge. And there also exist examples where there exists a cut edge, but not a cut vertex. And I kind of discussed those during this session also. And then in the eighth week, we continued this discussion of graphs and discuss some more properties. So first of all, we discussed what's an adjacency matrix representation for a graph. So it's just like ijth entry of the adjacency matrix denotes whether an edge is present in the graph between the vertices I and j. It's one, the entry, ijth entry is one. If the edges are present, it's zero if the edges are not present. This is what we call the adjacency matrix representation. And then we discuss graph isomorphism, like what do we mean by graph isomorphism? So a graph G prime is isomorphic to G if there exists a labeling of vertices of G such that G prime becomes equal to G. So what does this mean at a high level? That the graph G prime and G are isomorphic if they are actually the same graph. So not that they can be the same graph, but they might have different numbering of vertices, and so we might be confused and we might not know whether these are the same graphs or not. So it is possible that two graphs are actually same, but they are represented in such a manner that we do not see them as same, but they are actually same. So this is what we call isomorphism, that uh, a graph is isomorphic to another graph if there exists a labeling of first graph so that it becomes equal to the second graph, something like this. So we don't change any edges or vertices, we just change the labeling and then the graphs become equal. So this is what an isomorphic graph. And then we discuss what's a complement of a graph. So a graph has a complement of a graph is just a graph like a in which the vertex set remains the same, but we invert the edge set. So what do you mean? So what do I mean by inverted? So if in the original graph, let's say original graph was G and complement graph was G prime, then if there was an edge between two vertices in G, then G prime won't have an edge between those two vertices. And similarly, if G did not have an edge between some two vertices, then G prime will have an edge between those two vertices. So effectively, if a graph has n vertices, and so like it can be easily seen that if a graph has n vertices and m edges, then its complement will have n vertices and n choose 2 minus m edges. Because total number of edges in a graph can be n choose 2, and there are m edges present in G. So these m edges won't be present in G prime, and all other would be present. So n choose 2 minus m edges would be present in G prime. Then we discuss what are bipartite graphs. So a graph is bipartite if and only if it can it contains only odd length cycles. Okay, I think I wrote it wrong. If it contains only even length cycles, that's what we call it a bipartite graph. So bipartite graphs if are effectively the graphs in which the vertex set can be partitioned into two sets x and y such that all edges of the graph are between x, one endpoint is in x and other endpoint is in y. So no edges, no edges present in between two vertices of x. If there exists such a partitioning, then that graph is called a bipartite graph. And there's an equivalent formulation for a bipartite graph, which I just said that if a graph only contains even in cycle, every cycle of the graph is even, then that will be a bipartite graph. That there will always exist a partition such that uh, all edges go across the partition x and y, something like that. And then we discuss what are Eulerian graphs. A graph is Eulerian if and only if every vertex of the graph has even degree. So on a high level, like what are Eulerian graphs? So uh, Eulerian graphs are the graphs which have like an Eulerian tour. And what's an Eulerian tour? It's a tour in which all edges are covered exactly once. So if we have a walk or let's say a tour in the graph in which all edges have been covered exactly once, then that's what we call a graph is Eulerian. And there's a criteria like a graph is Eulerian if and only if every vertex has even degree. So if this is true, then the graph is Eulerian. If this is true, then every vertex will have an even degree. Such like that. And then what's a Hamiltonian graph? So Hamiltonian graph is a graph in which there exists a path which contains all the vertices. So note that a path does not have any repetition of edges as well as vertices. So if there exists such a path in the graph which contains all the vertices, then that's what we call a Hamiltonian graph. So yeah, and this path is called Hamiltonian path. And then we discuss these Dirac's theorem and Orr's theorem, which check whether the graph is Hamiltonian. Like Dirac's theorem, so you might remember the theorem. So Dirac's theorem was one theorem, and then Orr's theorem was a generalization of Dirac's theorem. And this states some conditions, like if this condition is true, then the graph is Hamiltonian. And note that there does not exist concrete generalization characterization like we have for Eulerian graphs. Like if everyone has an even degree, then the graph is Eulerian and so on. For Hamiltonian graphs, we don't have such characterizations. So what we say is we have some weaker results that, okay, so Direct theorem states some conditions. If this statement holds, then the graph will always be Hamiltonian. And similarly, Ohm's theorem is a more generalization of the Direct theorem itself, and also state that if some condition holds, then the graph is Hamiltonian. But note that these theorems, like they are not equivalent formulations of Hamiltonian graphs. Like, these theorems are just sufficient conditions, but not necessary. Like a graph can be Hamiltonian even if it does not satisfy this Direct theorem or Ohm's theorem properties. But if it does satisfy Direct or Ohm's theorem properties, then it will definitely be Hamiltonian. And this is how, like this is why it is just these statements are just sufficient, but not necessary. And then we discuss what are planar graphs. So planar graphs are graphs which can be embedded in a plane. And for these kinds of graphs, we discuss somewhat of is equivalent to Euler's identity, which we know like exists in geometry, which says that V plus R is E plus 2. It just says that number of vertices in the graph plus number of regions in the graph is just equal to number of edges plus 2. So this is what we call the Eulerian formula or Eulerian identity, that V plus R is equal to E plus 2. And this is true not for general graphs, but for planar graph. So maybe I should, yeah, put it like this. Otherwise, it might get confusing that this is for general graph, but there is no concept of regions in general graph. Yeah. And then in the ninth week, we discuss what are generating functions, how do we solve the generating functions, how do we obtain generating functions, and their various applications. These are one of the coolest things to exist in mathematics, and like, they help us a lot. And so like some of the generating functions, like so generating functions can be just thought of as expansions also. So 1 by 1 minus x can be expanded to be written as 1 plus x squared plus xu till infinity. So what do we say? The generating function for this sort of sequence. So know that the coefficients of all these powers of x's correspond to a sequence of numbers, right? If we write down the coefficients, then the sequence obtained is 1 comma 1 comma 1 comma 1 comma 1 and something. So what we say is the generating function for this sequence will be this 1 plus x squared plus x cubed and so on. And like this can be written succinctly as 1 by 1 minus x also. So yeah. Similarly, if we are given a sequence 1, 2, 3, 4, 5, 6, 7, 8, 9 till infinity, then if we again write it in the form of like polynomial, it will be 1 plus 2x plus 3x squared plus 4x cubed and so on. And again, this can also be succinctly represented as 1 divided by 1 minus x whole square. And similarly, like we discussed a bunch of generating functions, and yeah, the high level idea was this only, that generating function for a sequence is just a polynomial like in which the coefficient of x to the power n corresponds to the nth entry of the sequence. And then in the 10th week, after knowing about generating functions, we discuss some more advanced counting methods. So initially we discussed very primitive counting methods like permutations and combinations. But then in advanced counting, we learned about the principle of inclusion exclusion, which we also know since, which we might have also discussed in high school. You guys might have seen in high school, but note that we discussed some more involved problems about the same, like finding the number of onto functions from a set to another set and things like that. So principle of inclusion exclusion is also like very commonly used in computer science. So one of the applications is like this is a very common application, like counting number of possible onto functions. So yeah. And then like after discussing inclusion exclusion, like we also discussed about what are root polynomials and so on. These were like cool characterization of placing roots in a graph, but like not too difficult. So yeah. And then in 11th week, we learned about what is a recurrence, and like recursive relations are just like, yeah, we discussed what are recurrences and we saw different types of recurrences. And some of the recurrences which we saw were like Fibonacci and how do we solve Fibonacci, like how we saw some methods how to solve the recurrences also. And how to do this, we sort of form a polynomial for the recurrence, which we call a characteristic polynomial of the recurrence, and then solve it and find its roots and do some stuff. So we saw what are Fibonacci series, like these are sort of recurrence in which like the nth term is just the sum of n minus 1 plus n minus 2th term. And then we saw how to solve the Fibonacci series. And like in general, we saw how to solve the recurrence in general recurrences. a number of recurrences. Like all recurrences can't be solved, but we saw like some of the recurrences which we can solve. And then we saw like the Tower of Hanoi problem, which is again related to recurrences. And we saw the solution to it also. Similarly, we also saw what is merge sort, which is a recursive procedure for sorting numbers. And it's like very fast, in fact, it's like it has a order n log n time complexity. Like it's much faster than other sorting algorithms, like, other than split sort. So yeah. And then in the last week, the 12th week, we just discussed some concepts related to group theory. So what is a group? So groups just consists of a set and a binary operation defined over elements of that set. So, and like this, like just this is not sufficient to define groups. So there should be a set and a binary set operation defined over elements of the set such that the following four properties are satisfied. So four properties, the following four properties also need to be satisfied for it to be called a group. And the properties are associativity, closure, existence of identity, and existence of inverse. And these properties, like guys already know, like what are these properties? We have already discussed these. So if these four properties are satisfied by the binary operation and the set, then this set and binary operation is called a group. Otherwise, it's not a group. And what's a finite group of so what's order of a finite group? So it's like just the number of elements in the group. So first of all, like I should define what a finite group is. So finite group is a group in which number of elements is bounded. Like this set. So this set of the group, like the number of elements in this set of the group should be bounded. Like it should not be infinity. And if this is the case, then that is what we call a finite group. And order of a finite group is just the number of elements in this set. So number of elements in the group is what we call the order of a finite group. And then what are subgroups? So subset of a subgroups are just subset of a group which follows the same group properties over the same operator. So note that I've written the same operator in bold because some people can argue is okay, like suppose we have a set, like I kind of gave this problem in the problem session also, I believe. If we are given a set and a binary operation, and let's just take a subset of this set and define some other binary operation, and then such that that operation follows these four properties, then do we call that a group? But that is not the case. Like actually, the subset should be like the set which we take in a subgroup should be a subset of the original set, but the binary operation should be the same. That's why I'm saying over the same operator. And if a subset also satisfies the following four group properties, then that's what we call a subgroup. So it's just a group within a group, and that's why we call it a subgroup. And what does Lagrange theorem says? So Lagrange theorem says that order of a subgroup is always a divisor of the order of the group. So note that right now, if we are defining order, we are just defining it with respect to finite groups. So with respect to finite groups, Lagrange theorem says that the number of elements in a subgroup will always be a divisor of the number of elements in the original group. This was one of the last things which we discussed in this course. So yeah, and there were problems which we discussed regarding it. So okay, I guess this was all the notes which I had to discuss for this session. Like so, this is supposed to be a 1 hour session, so we are quite on time right now. So yeah, guys. So I'll be sharing. So I'll be like uploading these notes also on the like drive link which you might have, and this video also on the YouTube session on the YouTube channel. So I guess you guys can see this so that it helps in your revision. So yeah. So this was our last session. Like this was our last session for this semester, guys. So it was like nice interacting with you, although no one is present in person in this session. But just thanks to the YouTube audience for watching all these sessions. And I hope your NPTEL exam goes well. So yeah, all the best for the exams. And yeah, so I'll just be like disconnecting the world. So it was fun interacting with you guys in this session. Hopefully we'll see you guys next semester also in some different course. So yeah, till then, goodbye guys.